Hi, in this video we're going to be talking about eigenvectors and eigenvalues again. We have a transformation applied to a vector is equal to lambda times a vector. After we choose a basis, we can turn that into a matrix. So if we're looking for the eigenvectors and eigenvalues for a transformation, all we have to do is choose a basis, we get a matrix, and we can find the eigenvalues and eigenvectors for that matrix, and then we can translate back. When we translate back, the lambda value is going to be exactly the same. These two lambdas are literally the same thing. The vector over here is written with respect to this basis, and then we could just multiply its corresponding coordinates by the basis vector, like always, to translate it back into some vector in our abstract vector space. So what happens if instead of choosing this basis to get us this matrix A, maybe we choose a different basis? So what that's going to look like is it's going to give us another matrix. This matrix is still going to correspond to this transformation T, but it's going to be with respect to a different basis. And we're still going to want to look at this equation, BV is equal to lambda times V. So this lambda that we're getting out of this, it doesn't care what basis you choose. This lambda will be the same if you choose this basis or if you choose this basis or if you don't choose a basis at all. This is an inherent property of the transformation itself. The vector that you're going to get out is going to look completely different up here as it does down here because this vector is written with respect to this basis and this vector is written with respect to this basis. They are technically the same vector if you account for the basis, but the coordinates that you're writing them down in as elements of Rn, they look different. So I'm going to call them both V, but they are different looking vectors. So let's look at this equation. So remember that the determinant of A minus lambda I, we want that to equal 0. This is the characteristic equation. Okay? And if your vector space is finite dimensional, which all the ones we'll be working with are, or at least for the ones with eigenvalues and eigenvectors, the problems that we'll be dealing with will all be finite dimensional. In other words, A is some n by n matrix and n is a finite number. As long as that's the case, then the determinant of this will always be a polynomial. So this piece right here will always be called the characteristic polynomial. Now we have a theorem. So if A is similar to B, then A and B have the same characteristic polynomial. So just recall, A is similar to B means that there is an invertible matrix P so that B is equal to P inverse times A times P. And there's multiple ways to write this. You could write it like this, or you could say A is equal to P inverse times B times P, or you could switch the inverse to the right side instead of the left. All of those things are equivalent, maybe for different P's, but the existence would still be equivalent. The existence of an invertible matrix P. So why is that relevant to what I just did up here? Well, this invertible matrix P is the change of basis matrix. So if you wanted to switch from looking at the basis that you chose up here to get to A versus the basis that you chose down here to get to B, there is a relationship that looks like this for P being the change of basis matrix. So having two different bases is going to not change the characteristic polynomial. And if you don't change the characteristic polynomial, remember lambda is the set of lambda that you're looking for is the set of solutions to the characteristic equation. And if the characteristic polynomial is the same in both of these cases, then the lambdas will also be the same. Okay? So why is this true? Recall that the determinant of a product is equal to the product of the determinants. And finally, recall that A times the sum of two matrices, so these are all matrices here, A times the sum or difference of two matrices is equal to this thing where the A is distributed in. So this is left distributivity, and this second equation down here is right distributivity. So you can distribute from the right or from the left, and as long as you keep the same order here, so A is on the left side of these multiplications, whereas C is on the right side of these two multiplications, as long as you have that, then these will be true. Matrix operations are both left and right distributive. So now let's prove this theorem here. So I want to say that these two have the same characteristic polynomial. And so I'm going to start out with the characteristic polynomial of B, which is, remember, the determinant of B minus lambda I. So we have the determinant of B minus lambda I, and the very first thing I'm going to do is replace this B here with P inverse AP. So I know there is an invertible matrix P so that this works. So I'm leaving off the part where I quantify this and say that there exists a P blah 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 and just using it. Okay, so that's the first step. And it would be nice if I could just use this multiplication property and split this up. But this isn't quite right, so I can't quite say this is the product of two matrices yet, or three matrices for that matter, because we're subtracting something off. So what I want to do is I want to adjust this right thing so that it has a P inverse and a P in it that I could then factor out using the distributivity laws. So I'm going to rewrite this as so I'm first going to write it as lambda times P inverse times I, and then times P. But that's the same thing as just saying this. Okay, so let's look at both of these steps that I just did. So this one says that I can replace I, this matrix that I had here, with P inverse times I times P. Now if you think about just multiplying these three matrices together, well, I times P is just p, and then p times p inverse is just I. So replacing I by the product of these three things is not going to change anything. Okay. This second thing that I did here says I can just move the lambda back into the inside next to the I, and that's true because constants can always be moved past matrix multiplication, right? Constants commute with all matrix multiplication. Okay, well now I can use my distributivity properties and say both of these two things that I'm taking the difference of here have a p inverse on the left side, and also both of them have a p on the right side. So I'm going to use both of these properties at the same time to rewrite this matrix that I'm taking the determinant of as p inverse times some stuff, and then times p. So I'm factoring out a p inverse to the left and a p to the right. And what's left is, well, this term just has an a left in it. So this first term is p inverse times a times p. And the second term is just going to have a lambda I. Okay, so the sign stays the same. And the second term is p inverse times lambda I times p, which is exactly what it was. Okay, at this point, I have the product of three things that I'm taking the determinant of. And according to this formula, if you take the product of two things and then take the determinant, that's the same thing as taking the determinant of each one and then multiplying the answers together. And the same thing works for 3, right? I could just pretend that b itself is the product of, say, c times d, and then I'd have a c times d right here, and then according to this formula, I could then break that up again. You get the product of 3 things. So whether there's 2 or 3 or 15 things, you can always break it up. The determinant of product is the product of the determinants. So this is the determinant of p inverse times the determinant of a minus lambda I times the determinant of p. And now one more property of determinants that we need is that the determinant of p inverse is the multiplicative inverse of the determinant of p. In other words, these two things are going to cancel. They always multiply together to be 1. And that leaves us with just the middle term, which is the determinant of a minus lambda I. Okay, so what we just showed is that the determinant of b minus lambda I has to be equal to the determinant of a minus lambda I, which proves that they must have the exact same characteristic polynomial, and therefore they have the same eigenvalues. Here's a proposition that says if A is a triangular matrix, then the diagonal entries of A are the eigenvalues of A. So this is very useful in terms of a shortcut. If you happen to have a triangular matrix, then you can easily read off the eigenvalues without having to do a long calculation. So recall that a triangular matrix is one where either all the entries below the diagonal are 0 or all the entries above the diagonal are 0. So this one is called upper triangular because the non-zero entries are above the main diagonal. So let's take a look at this. We have -3, -2, 6, -2, and 1. So -2 is repeated twice. So we can say that the eigenvalues are exactly the numbers on the diagonal, and then -2, because it's repeated twice, has multiplicity 2. Now eigenvalues, just like with roots of polynomials, can have multiplicity, and it literally means the same thing in terms of the roots of the characteristic polynomial. Okay, so let's see why this is the case, and I'm only going to do it for this one matrix here, but it's general enough that you can apply this to any arbitrary matrix. It's just the notation gets a little bit rough if you do. So here's the matrix A minus lambda I that we want to take the determinant of. And remember that all we're doing is just subtracting lambda off of all the diagonal entries, leaving the rest exactly the same as it was. And one of the properties of determinants that we can use is that you can always take a cofactor expansion. That is to say, you can choose a row or a column and then expand out the formula for a determinant based off of smaller determinants. The formula for how to do this is Theorem 1 in section 3.1 of the book. So let me tell you what it says for this particular case. I'm going to choose this first column here. And the reason this is useful is because this first column has a bunch of zeros in it. So most of the pieces of that equation in the theorem that we're using are going to be 0. Okay? So what it says is the determinant of this whole thing is equal to this entry times the determinant of this 4x4 smaller matrix, which I have written right here, and then plus 0 times the determinant of another 4x4 matrix, minus 0 times the determinant of another 4x4 matrix, plus 0 times the determinant of a 4x4 matrix, minus 0 times again, and plus. But they're all 0. Okay? So what it boils down to is you just copy that thing down and then take the determinant of this, which is another upper triangular matrix. Okay? But then you can keep doing this. The determinant of this is negative 2 minus lambda times the determinant of this 3x3 matrix, and then plus and minus a bunch of zeros. Okay? And then you keep going like that, and eventually you'll get down to just the determinant is the product of these things. Notice that this is exactly what it means to have all of these lambda values be the diagonal entries, right? This is 0 exactly when lambda is negative 3. This is 0 exactly when lambda is negative 2. And look, we have 2 factors of those, so multiplicity 2 for that one. Let's look at this slightly nasty example. So we have this 3x3 matrix A here, and I want to determine the eigenvalues. So I'm going to take the same matrix with lambda subtracted off each of the diagonal entries, and then we're going to take the determinant of that. And remember, the determinant of a 3x3 matrix can be found by doing something like this. So if you're trying to find the determinant of this, what you do is you copy down the first and second columns here. So A, D, and G, B, E, and H. And then you do this. You do A times E times I plus B times F times G plus C times D times H. And you take that sum of 3 things, sum of 3 products, and you subtract off CEG, and then you subtract off AFH, and then you subtract off BDI. So it's the sum of the purple things minus the sum of the green things. So all the green things have a negative sign, all the purple things have a positive sign. So what we get is something like this. So this is the sum of the positive things here. So this is the main diagonal. And then 2 times negative 3 times 2 is negative 12, and we're adding that on. 3 times negative 1 times 4 is also negative 12, and we're adding that on. And then we subtract off the opposite diagonals. Okay, so this is a little bit messy. I'm going to assume you're comfortable with doing some nasty polynomial algebra. Factoring can be a bit of a chore. It's mostly just a guess and check is the most efficient way to do this. Remember, you have Wolfram Alpha or whatever other online source you want when you're doing a homework problem. As far as tests and quizzes go, you won't have something with nasty numbers like this, so you don't have to worry about that. You'll probably only have 2x2 matrices or very simple 3x3 matrices, or one where I just tell you the eigenvalue and you don't have to worry about doing this step. Okay, so regardless, I want to focus on the fact that this lambda equal to 3 has multiplicity 2. So we're just going to look at the lambda equals 3 case and ignore the lambda equals 8. And we're going to take a look at the null space of A minus 3i. Okay, so the null space is the same as the set of eigenvectors, with the exception of the fact that 0 is not supposed to be an eigenvector, but 0 is in the null space. So they differ by having the 0 vector or not, but it's essentially the same thing. So we have right here, this is this matrix right here, where lambda is replaced by 3, and then I actually did the subtraction, so 4 minus 3 is 1, etc. So I've augmented that with zeros on the right-hand side, and notice here that we have this row is just -1 times this row, and the last row is twice the first row. Okay, so we can clear off the second and third rows here and just get all zeros. And if we call this the number of A's, B's, and C's, then we know that A plus 2B plus 3C must be 0. That's what that top line says. Okay, and then we can solve for A, or solve for whatever variable you want. And now we can write this vector ABC as, well, B and C are free variables, so those are just what they are. But whatever A is, it has to be -2 times B minus 3 times C. Okay, and now we can take that and separate out the B and the C and get the dimension of the null space as 2, and here is a basis, this vector and this vector. Okay, so this null space is the linear combination of these two vectors here. So what can we say? Well, not only do we know that this vector and this vector are eigenvectors, with eigenvalue lambda equals 3. But we can also see that these are linearly independent, and in general this process is going to give you linearly independent vectors here. And these form a basis of the null space, and when you're looking at this particular matrix that you're taking the null space of, A minus lambda I for some lambda, then this has a specific name. So this right here, this set, is a basis for the null space of that special matrix there. And the null space of that special matrix is called the eigenspace. And I will call it the lambda eigenspace. For lambda equal 3. Okay, so the eigenspace is the set of eigenvectors for a particular lambda value, and lambda has to be an eigenvalue for this to make sense. And then it also includes 0, right? It's everything in the span. So in the eigenspace, we do include 0, but technically 0 is not an eigenvector. The lambda eigenspace is the set of lambda eigenvectors along with the 0 vector. Here's one non-example. So recall that we showed that if A is similar to B, then A and B must have the same characteristic polynomial. And here is a case where A and B are not similar, but they do have the same characteristic polynomial. So these are both upper triangular, and so the characteristic polynomial is just the diagonals minus lambda, all multiplied together. So 1 minus lambda times 1 minus lambda, and this is the exact same thing, 1 minus lambda times 1 minus lambda. If you think about doing this with an actual calculating a determinant, remember for a 2 by 2 matrix, the main diagonal gets multiplied together, and then you subtract the off diagonal getting multiplied together. But because there's a 0 down here in both of these matrices, the off diagonal is just 0, and so you only have to look at the main diagonal. Okay, so why are these two not similar, despite the fact that they have the same characteristic polynomial? Well, this one's the identity matrix, and in general, the identity matrix is never similar to anything other than the identity matrix, right? Think about similarity as representing something else in a different, or representing the same thing in a different basis. And the identity transformation represented in a different basis should still be the identity transformation. It should still not do anything. So that's one way to say it. Here's the actual matrix definition that we have. So remember, similarity says that one should equal P inverse times the other times P for some invertible matrix P. And I want to just state that if you have the identity in here and you multiply it by P, then this product right here is just P. The identity times P is P. And you multiply P by P inverse, you should get the identity. And this cannot be equal to something that is not the identity. Therefore, this matrix and this matrix cannot be similar to each other. Okay, so they're not similar, but they have the same characteristic polynomial. So this implication that we have right here does not go backwards. It is not the case that if you have the same characteristic polynomial, then you are similar. So we cannot go the other way. Okay, now I want to briefly talk about the invertible matrix theorem. So we have two new parts to this, part S and part T. Part S says that 0 is not an eigenvalue of A. So remember that 0 being an eigenvalue says we subtract a 0 off of the main diagonal. In other words, we don't change it. And then we want there to be a non-trivial solution to AX equals 0. So if there is a non-trivial solution to A minus 0 times lambda x equals 0, then that's the same thing as there being a non-trivial solution to A times x equals 0. And if there is a non-trivial solution to A times x equals 0, that means the matrix cannot be invertible. Okay? And that's exactly what it means for the matrix not to be invertible. There's a non-trivial solution to AX equals 0. Okay. That's part S. Now part T. Part T says that the determinant is not 0. So the determinant, if you think about the determinant of, say, a 2 by 2 matrix, and what that does to a square, so if you take just the set of vectors in R2 that are inside of the unit square, so their first coordinate is between 0 and 1, and their second coordinate is between 0 and 1, and so we get this square, and then if you apply some matrix to that square of vectors, it's going to shear it, possibly rotate it, and then maybe stretch it out a bit. Okay? Whatever you get out is going to be some parallelogram, and the area of that parallelogram is the determinant of the matrix that you applied to get to it from the original square. Okay? In general, if you use a square that is not a unit square, you then also have to multiply by the area of the original square that you had. The same thing works for 3 dimensions. If you want to calculate the volume of what happens to this cube here, so I called this cube S, and it's the set of vectors so that all 3 of the coordinates are between 0 and 1. That's just the standard unit cube sitting in the first quadrant. And if you want to apply a matrix A to that set S, then what you're going to get out is the set of vectors in R3 such that each of the vectors in there is equal to A times S for some S in here. So it's the set of images of the cube, of the interior of the cube. Interior and the boundary, I should say. So this new set, so it's going to take this cube here that's spanned by, or I should say it's the inside of the hull of E1, E2, and E3. Okay, again, just all the coordinates are between 0 and 1. And it's going to take it and it's going to figure out where E1, E2, and E3 get sent, and it's going to do the same sort of construction where you still want all the if you write a linear combination of these three new vectors, you still want all the coefficients to be between 0 and 1. So it's the same setup. The shape you get out is called a parallelepiped, and it's the same sort of, you want to shear the cube and then possibly rotate it and possibly stretch it out. And one thing we can say about that is the volume of the new shape that we get out is the determinant of A times the volume of the original thing that we started out with, which in this case was 1. Okay, so the determinant of A is the volume for this particular S that we have right here. Now, why does that mean that determinant not being 0 means that the matrix is invertible? Well, what would it mean for the determinant to be 0 here? If the determinant is 0, then that means the new volume that we get out is 0. In order for a three-dimensional object to have volume 0, we must have flattened it in some direction. So there's some dimension that we don't extend out into. So in this example, what that would mean is that all three of these vectors would have to lie on the same plane. Okay? And that would exactly mean that the matrix is not invertible. Okay? If the matrix, so going the other way, if the matrix is not invertible, then there's some linear dependence between the columns, and you end up, given that linear independence, that some set of those vectors that you reach lie on the same plane, or the same lower dimensional subspace. Okay? Which is going to imply that some higher dimensional notion of volume is going to be 0. So we have volume for 3 dimensions, we have area for 2 dimensions, we have length for 1 dimension. There is an n-dimensional notion of volume that I don't want to get into, but it's essentially saying the same thing. So this is just an intuitive way of grasping what the determinant is in general. It's measuring the change in volume when you apply a transformation to a 3D or n-dimensional object. So having something get smushed down is the same thing as having the determinant be 0. And that's exactly what it means to not have the matrix be invertible. Thank you for watching.